Okay.
Good morning, everyone. My name is Carlos Sanchez. I'm a geotechnical engineer based in the BGC Vancouver office, and my main focus is the design and operation of tailings facilities. So it is my pleasure to introduce our next presenter, Caio Stringari. And Caio will be discussing an innovative application of satellite imagery and machine learning to conduct a bathymetric survey for a tailings dam. So for those who are not super familiar with tailings dams in the mining industry, bathymetric surveys are crucial to estimate the storage capacity, but also how much water is accumulated in these large structures. And those are two fundamental requirements for the safe operation and planning of these facilities. Caio is a coastal oceanographer and data scientist in BEC Vancouver office. He has over 10 years of experience working with nearshore processes such as waves, currents, and coastal erosion, and he has published several papers on remote sensing.
Thank you very much, Carlos. Can you guys hear me okay? I hope so.
Yep.
If not,
Yeah,
please let me know. All right, let's start my presentation. Okay, so my presentation is entitled Estimating Tailings Dam Bathymetry Using Multispectral Satellite Imagery and Machine Learning. And I'd like to acknowledge my co-workers, Janine Engelbrecht and Brett Eaton, who helped with this project. I am currently with Cambio Earth Systems, which is an offshoot of BGC Engineering. And this research project was actually funded by the Canadian Space Agency under the Smart Earth initiative. So just a fresh reminder for those who are not familiar with tailings storage facilities. So they are facilities that are engineered to store byproducts as known as tailings during any mining operation. So pretty much any mine is going to have a tailing facility. And tailings are leftover materials from the mining process, and those cannot be released in the environment and then have to be stored, and consequently we have this purposely built structures. And one commonality is that they have a pond, and that pond has water, and if that pond has water, we have to manage that. And there are a lot of them. So there are about 20,000 tailings storage facilities worldwide. They are usually very well managed. The failures are not common, but they do happen, and when they happen, the consequences are grave. So we have to manage them well, and managing the water inside of those facilities is a very key factor in any mining operation. And why we monitor? We monitor because we want to avoid situations like these. So like these are big dam breaches that happened in the past. I gave a very similar talk at the Canadian Remote Sensing Symposium a few months ago, and just a few days before that symposium, there was a headline that there was a tailings failure in the Philippines, and 55 families basically lost their houses. And in severe cases like Brumadinho in Brazil, many people died, and we really want to manage and monitor this facility so things that like this don't ever happen. So what is our objective here? What was the goal, and how is actually currently done? So our goal here is to develop a method that we can basically measure the bathymetry or the depth of the storage facility pond from space using satellite data. How it currently is done is by boat surveys. So we have surveyed boats with a mostly likely a single beam echo sounder that's measuring the bathymetry. In more recent years, we're moving away from manned boats and using AUVs instead. Each of them have their own benefits and disadvantages. There are occupational health and safety concerns when you're doing this type of surveys. If you have a manned survey, you are exposed to hazard materials, and ideally we want to avoid that. If you're boat is too large and your pond is too shallow, you probably would not be able to survey the shallow parts of the pond. And if your tailings is too large, it's going to take a very long time to survey the facility, and you probably won't be able to do that in a single day. So our goal here is actually to use satellites to do that, because you have an entire view of the entire pond at once, which should save a lot of time. And how, like, why can we do that? Like, what's the physics behind this that allows us to do that? The physics behind this is the differential absorption of wavelengths in water. So more, if you take the visible spectrum, or actually not the visible spectrum, only the entire radiation spectrum, different wavelengths are absorbed differently by water. So high energy wavelengths like blue and the greens and the violets and the ultraviolets, they penetrate much deeper into the water compared to yellows and reds that get scattered very close to the surface. So this differential absorption of radiation actually allows us to create a proxy to uh, estimate the bathymetry. And because satellites like Sentinel and Landsat gives us these different bands of wavelength, that we can use that to build a model to actually predict the bathymetry. And there has been many studies, mostly in rivers and coastal oceans, that have exploited that fact to estimate bathymetry. However, there are not many applications of this technique for mines. We found just a few studies, mostly more prominently, I'd say, this study from 2016 that investigated one tailings facility. But there are many studies for coastal oceans in particular. So one of our mining partners was very kind to provide us with bathymetry data for a mine in British Columbia. And we constrained ourselves with acquiring satellite, like public satellite data, within a few days of the observed bathymetry. So in the end, we end up with a data set that has 3 days for Sentinel and 4 days for Landsat, and we're going to try to use that to build a model. Our design is a very typical design of a machine learning or a data-driven experiment. We have satellite data, we have survey data. We split that data in the 3 different data sets that John just mentioned, like training, validation, and test data. And then we train a model. That model can be anything, really. It can be an empirical model, it can be a physical model, it can be a deep learning model. And the goal of that model is to actually predict the observed bathymetry, or I should say the surveyed bathymetry, as best as it can. So in the classical machine learning spectrum of things, that we tried 3 different models. We tried a model called XGBoost, which is a model based on decision trees. We tried a old school neural network in the form of a multi-layer perceptron. And we tried a genetic programming model as well. These models differ in how they are programmed, how they work, the results that they provide, the intermediate steps, and so on. So I'm not going to go into the details of each model. And long story short, the XGBoost model, the decision tree based model, is the best model of the classical machine learning models. And I'll show the results only for that model. The multi-layer perceptron got really close to XGBoost, and the genetic programming model was a bit of a failure. It was actually not very good at all. In this presentation, I'll focus on the decision tree models. So for Landsat here, we obtained a difference between observed and predicted bathymetry on average in the order of 8 centimeters. So the error of the model is really low, so less than 10 centimeters. And if we look at the graph on the right, bottom right corner here, we have a scatter plot between the surveyed bathymetry and the predicted bathymetry. A perfect model would have all the points following in this red line here, which is the 1-to-1 line. And if we look at the counts of the predictions, all the counts align very close to the 1-to-1 line, with only a few scattered dots outside of the 1-to-1 line, which is a very good indicative that this is a good model. And if we look at spatially where the model is performing worse, is around the areas that are shallower or close towards the edge of the pond, where because we're using like pixel data to make the predictions, those pixels close to the edge of the pond probably have a mixture between like land and water pixels, and that confuses the model a little bit. So overall, XGBoost with Sentinel-2 data provides really good results with mean average errors around or less than 10 centimeters. We can do the same thing for Landsat. Landsat has less resolution than Sentinel, so Sentinel is at 10 meters resolution and Landsat is at 30 meters. We get a very similar picture. The errors are a bit larger because of the lower resolution, and the results look a bit blockier as well, again, because of the resolution. But overall, we have a similar trend here in the results. The areas towards the edge of the pond saw the highest errors. One cool thing about the XGBoost model is that it gives you a metric called feature importance, and that is pretty much what made the model make those predictions. Like, what was the most important variable in the model for those predictions? And we see that that's coastal aerosol, the coastal aerosol band, which is a very high energetic band, close to the blue band, which means that's the band that predicts most, penetrates most into the water. So that's a good indicative that although this is pretty much a black box model, there's no physics in it. The model is kind of sniffing a little bit of the physics of the process, and that was a reassuring result for us. But can we do better? We tried. We tried. Next step was to use a deep learning approach. So we used a very simple convolutional neural network here. It's a very shallow network, and instead of feeding the entire image to the neural network, because we only have like pretty much 7 data points, we actually feed subsamples of the image to the neural network and try to make predictions on that. And this is what it looks like if you apply the neural network considering those windows to the whole facility. And we are here is lighting the window across the image and creating a prediction for all those windows. And if we keep doing that, we will eventually predict the entire pond. After we do that prediction for the entire pond in windows, we actually interpolate the results, and we get a very similar picture that we got before with XGBoost, where we have a model that has pretty low errors overall, and the highest errors are close to the edges of the pond. Because of the interpolation process, the bathymetric surface here is a bit smoother than before, and that is a bit debatable if it's better or worse, but because of the interpolation step in the end, it makes a smoother surface. We can do the same thing for Landsat. We get similar results. Again, a little bit blockier, a little bit the errors are a bit higher in this case. Actually, again, the resolution of the data, satellite data here plays a lot of plays a big role here in how good your results are. So if we look at the results in general, we see that for Sentinel-2, the convolutional neural network had the lowest errors, with mean absolute errors in the order of 6 centimeters, which is pretty low. And for Landsat, actually, the XGBoost model was better. Another advantage of the XGBoost model is that it's really fast to train. It's really easy to use. Only takes a few, I'd say, seconds to run and train, whereas the neural network model takes a few hours on a very good computer. So yeah, XGBoost model, really good. So what are the opportunities and limitations here? We demonstrate that the concept works. We achieve errors on the order of 6 to 12 centimeters. Higher resolution data provide better results which indicates that we've used satellites with even higher resolutions, such as WorldView 3, the results would be even better. Because we can image the pond at once and the entire pond, it's much faster than a conventional bathymetry method. And there is an opportunity to combine a satellite survey with regular bathymetry, so you end up with a hybrid product, which should be like the best of the both worlds. And our limitations are like we only test this at a single mine, so our training sample training sample size is pretty small. Atmospheric conditions such as cloud cover and suspended sediments will remain problematic. In this case, the model didn't have too much trouble with suspended sediments, but we foresee that for different mines and different conditions that will start to become a problem. And a little bit bringing back to John Danielson talk, bathymetric surveys are not entirely true. So they're also prone to inaccuracies and noise. So if you're training your machine learning model with bad data, you will end up with a bad model. So we need to consider that. And we hope to further research in this topic. So if you have data and are interested, please reach out to me and Janine. So our contacts are here in the last slide, and I'm 30 seconds over. So thank you very much, and happy to answer any questions that you guys have.
Thanks, Caio. That was an awesome talk. There are some questions in the chat that hopefully you can look at in the next little bit. We'll also post your email in the chat as well, and if folks have questions, they can reach out to you directly.